Till now, we have understood the directional aspect in detail, why it happens, and how we can make use of conservation of energy to explain it. Now we're looking at the magnitude aspect of EMF. So in the last video, we understood what is motional EMF. It's nothing but movement and voltage, right? Now, let's derive an expression. So the aim is to derive an expression for motional EMF by changing the area of the coil linked with a magnetic field. So here in this diagram, we are looking at a magnetic field. We have a wire, and on that wire, we have another metallic strip. So let me put it this way. We have a wire which is stripped. That is basically it is exposed wire, right? And on that running is a metallic strip. So at the top and bottom, we have a magnet. So basically, you can think of it in this way. So we have this setup, and we have a magnet, the top and bottom, say north and south. Something like this, guys. Got it? So what is that we are doing? We are making it pass through the bunch of magnetic field lines. And so by doing this, we are changing the area that it encloses. So we are looking at change in magnetic field lines. That is nothing but change in flux, and change in flux leads to induced EMF and current. That's all. Okay, guys. So let's consider a straight conductor moving in a uniform and time independent magnetic field. So it's constant. Figure shows a rectangular conductor PQRS, in which the conductor PQ is free to move. The length PQ is free to move. The rod PQ moves towards the left with a constant velocity v as shown in the figure. Assume there is no loss of energy because of friction. Again, we're looking at ideal scenario. Now, the flux will be given by what? The strength of the magnet into the area. Right? So we have seen this. That's nothing but the basic idea of flux. How many things are going within a given space? It's a product of that. As per the diagram, your area can be written as length into breadth. Simple. I'm not done anything fancy. I just made use of the definition of flux and made use of the figure. So here A is the area, and L and X are your length and breadth of that particular scenario. So change in area. If the area of the coil changes with time, the flux also changes. Let's denote the area as a function of time. So A of t. So Faraday's law of induction, right? According to that, we have the EMF, which is equal to minus d phi by dt. Now, since the area is changing, that's how we are changing the flux, right? Let me do that. Let me substitute. So this is BA divided by BT. But B is constant. So minus B dA by dt. So in this case, A can be written as Lx dt. Right here, B is constant. Because your magnet is constant, the strength is constant. And area can be written as length into breadth, but length is again constant. So dx by dt. Length is constant. Agree? So PQ length is constant. Now, what is dx by dt? Rate of change of distance with respect to time. That's nothing but your velocity. So that's your expression. That's your final expression. Basically, we are telling that how fast things are changing, the EMF will increase in that manner. Faster the change, better it is for the EMF. You got it? Does it make sense? Longer the wire, better it is. Stronger the magnet, better it is for the EMF. all of them make sense. Everything can be just understood common sensically. So don't just remember formulas, derive it in your head, and it should make sense. Every variable should make sense.